Hey everyone, how are we doing? Who's all here right now? I feel like my chair's a little low. Is it? No, chair's all the way up. Chair's all the way up. Who's here? Say hey in the chat. If you got questions, let me know. New assignment posted, new activity posted. What do we have? We're just hanging out right now, seeing what's going on, looking around, drinking our coffee. If you're here, say hey. I think we're streaming online. I think we are. There's a button I've been wanting to make on my Stream Deck. A realign Windows button. Let's look. Where is that? I'm gonna see. So we'll wait for questions to come in. Stream Deck button. Align Windows. There's an align Windows button. I do it. Automatic Windows functions. Elgato Stream Deck. So 1 minute. Shortcuts for Stream Decks. 5 hidden Stream Deck tips. Oh, I think he showed me that in that video. I think I was watching his video. Oh, we just started working on assignment 4. What do you have right there? I got a guy's video in the background here. He's talking about the Stream Deck. What questions do you have? They've got so many hints and tips for the Stream Deck. Windows Mover Resizer. Where do you get that? Because I've been meaning for that. This is where I saw it. I'm going to have to go find this out this weekend. Okay, that's on my to-do list. Let's see what questions there are. If you have questions, Kirsten, let me know. I've got this guy's video right here. 130,000 views on his video. And he's got a small channel for that many views. I mean, not that small. He's got about 80,000 viewers. But his gotta watch his video and got to learn how to do this Windows Resizer thing. It's going to take a little bit of time, it looks like. He goes through, Yep, so I need to do that. That's going to be a big help. Showed here in the background, but it has like get current Windows coordinates. And so that's going to be a huge help for what I'm doing, because usually I do a lot of clicking around to get like my windows placed around. So let's go show that. He's got right here on this device I use, there's a whole like get the Windows coordinates. So you can go here. There's the guy telling about how to do everything. Nice setup. Got some good purple light and everything around. And then Windows Resizer. It looks like he's adding it to the Stream Deck. A lot of fun ins and outs. And so what that's going to allow me to do is with one button click, I'll be able to like resize my windows, because you'll see a lot of times I'll be realigning windows. But rather than me moving things around on my own, I can just hit a button and it's like boop. And I'll probably have that here on my main screen, just be like doop. And then it'll just re-put my windows the way I want it. Or I can have it that it'll bring up certain things on the main screen. Yeah, that'll really help. I need to set that up this weekend. It's just all these utility things that I use to make things better, to make things stream better. Like I can show my back screen right here. I can go like, there's the screen right there. There's the high. I can disappear, and all this is just the time it takes to set up stuff. So we could just watch this full video right there on the main screen. We'll put him to a better. There we go. Much better still than right there. There you go. But no, all that awesome stuff just takes a lot of time, a lot of work. What are we working on with assignment 4? Let me get assignment 4 pulled up right here. What questions are there? I need to make sure I leave this on my screen. Bring it over here to the other screen. So that way I can work on that later tonight. Get that fixed up for my own streaming. If you're here and you have questions, let me know. We got 4 viewers right now, 201, 320. Feel free to ask anything. Question 4, what are you looking at? Which one are you working on? Windows Resizer. It's not one of the defaults. You have to go download it, do you? Do I have it? Oh, let me type in here. Can we over question 2? You bet. I just broke it. I literally... Stream Deck is currently crashing. Oh, literally... Stream Deck. Literally, I just crashed the Stream Deck. So it wasn't... Close the program. Okay. We'll let this... Okay. Is it working now? Oh, buddy. 2 seconds. Okay, I'm going to try to fix this. Okay. I'm reloading the Stream Deck. We're not going to do that right now. Let's go over question 2. Stream Deck looks to be working. Ooh, Stream Deck is not working at all? Okay. We're not going to work on this right now because apparently I'm crashing it, and let's not crash it. Let's go ahead over here and look at the assignment. I don't have it currently downloaded. Let's go grab it. So let's go grab the assignment question number 2. Here we go to associations. Why was it doing all that indenting this morning? I have no idea why. Here it is. Here's the assignment. Question number 2. Exercise 6C on page 72. So we need to go get the homework packet. And let's go take a look at that. The homework packet is right here. I'll show where that's at. Homework packet's under the modules section. Make sure to be under modules and go to the homework packet right here. There's the homework packet. Download the homework packet and open up the homework packet. And here we are. We need to go to page 72 and we're going to like 6C or something. So here we are right here. And let's see if we have the right question. It says exercise 6C on 72. Let's go ahead and just copy paste this and use it. Okay, so we've got the question. We're just bringing it over here to this world. And yeah, there we go. Here we go. Okay, so the question says, let's see what everyone's saying on the screen. This is what I'm trying to fix for later. Examine the association between bill and tip with the graphical and statistical output from the associate function. Which measure, Pearson versus Spearman, is appropriate for measuring the strength of a relationship? Is the relationship statistically significant? Does the choice of Spearman or Pearson affect this conclusion? Okay, so how are we going to write this out? I'm going to do a little bit of a different question right here. It wants bill and tip using the EX2 data frame. So if you run all this code right here, I need to replace this with a student ID. This is not your student ID, nor is it mine. I use 123. So we've got here just a random student ID, which is going to create a random subset for us. And let's take a look at the random subset and let's think about what we have going on. And the data frame we are using is the EX2 tips data frame, which is tips collected from a person at a restaurant. And they were looking at here at the tip they got, the bill that they had, the tip in USD the person had, the gender of the smoker, whether it was a weekday, what time of the day it was, and the size of the party. So I don't want to exactly do your question, but I'm going to do one very similar. So once again, don't do exactly what I'm doing, but kind of take cues from what I'm doing. When I examine this relationship right here, I'm going to use the associate function. Who knows the basic, I need in the chat, the basic form of the associate function. This is a classic thing we do all the time. Whenever we do associate, you always hear me say blank, tilde blank, comma, blank equals blank. So what do you always hear me say whenever we do the associate function? Because this will come into play when we do the LM, when we do the GLM, y tilde x. Trace, great job right there, some 20 points. Is Mubot awake? Let's find out. He is awake. He's talking in the background right now. Great job right there, Michaela also. Y tilde x comma data equals. It's funny, I brought in some 474s one time to a 320 class, and I was like, y tilde x, and they were like, comma data equals. And I was like, see, they know it. You use it so much. This is the formula format. I'm going to look at, let's go to names ex2 tips. And I'm going to take, I'm going to see if size of the party can explain how much people are spending, which I would think it would. This is not your question. Very similar, though. Like, if you can do this one, you can do the other ones. It's mad about the graphics right now. If you get that error, it's saying your window's too small. And I do like this one also. I like the way this graphic looks. I see a few things to point out. I see an issue as we go through. Let me draw on it. And I want you to tell me as I draw on this, what is Brian trying to highlight to you about this relationship? The first thing I'm going to draw here, I'm going to draw it in red pen. And I want to draw this. I want to draw this like this. And it going like this right here. So I'm talking about this. What am I kind of pointing out right here about this relationship? So I'm pointing out a few things about this. First thing I'm pointing out is this. What is Brian pointing out in red pen right there? Which is something to note for maybe we're better to use this. This is question 2, and it just asks us to do part C, I think. It says, do question 2, part C. So this is 6C. Well, it is monotonic. I do agree with that 100%, Trace. I 100% agree this is monotonic. But I'm trying to, with this right here, what am I, look at where I'm highlighting. I'm trying to more point out the what nature of the relationship. Thank you. What am I trying to point out right here with the nature of the relationship? It is nonlinear. It is nonlinear. But what am I trying to point out? Wait, take a look at, here, I'll make it even, the more obvious part of it's going to be this and this right here. It is nonlinear, but look at the specifics of this and this. There's a big difference in those. The proportional difference kind of, and what do we call this? We have stat 201 terminology for it. I'm talking about like this right here. Well, you're on the right track with where we're going to go with this. What graphically am I showing by saying it goes from this to this? Think stat 201, QQ, straight enough, no outliers. Or think about that fun word we've been typing out all today. What are we will go in this direction on this question, but what are we trying to illustrate by showing this right here? The vertical scatter, and the vertical scatter is differing, which is showing a differing in the strength, which is heteroscedastic, which is plot thickening in 201. 20 points, everyone. Great kind of walking through what are we talking about, what's going on right here. So there is some heteroscedastic differing in strength. It's getting weaker, then it's getting stronger again. And people are rightly pointing out, which I'll draw here next in the blue pen, that while it is monotonic, it is nonlinear. So a line does not well describe it. So that blue pen drawing, which I would do right here, would hopefully illustrate the nonlinear but still monotonic. And what do we mean by monotonic? It goes in one direction. As soon as it goes back down, it's non-monotonic. So monotonic just means one direction. Non-monotonic means it goes in at least more than one direction. Mono meaning one, tonic, directional. If that's what tonic stands for, I don't know. But it means one direction when we say monotonic. Monotonic, non-monotonic. Monotonic, non-monotonic. I want to do associative function for one of the questions I get. Cannot compute exact because of ties. That actually gets into, and that's such a great thing right there. So it's saying it can't get the exact p-value, but it will give you an estimated p-value still. So if you get that, you can still get the estimated p-value, but it can't give you an exact p-value. So it's such a great question right there, Michaela. It's still going to give you a p-value, but it's just saying a little more uncertainty than we would like, which is all right. There's always uncertainty. Statistics is about making good, educated guesses. So it's just saying, not 100% certain on this one, but who is? We never are. There's always assumptions and conditions and errors to have. So what do you notice right here? We see a nonlinear, heteroscedastic, meaning plot thickenings, change in strength, all that good stuff right here. And what does this scream to you then? So what this should be screaming to you right now, I get zeros, yep. But both are conclusive, yep. So it's a very statistically, in mine is too. Mine right here is extremely statistically significant for Pearson and also very conclusive on the result. And as Trace is pointing out, you can see even better now, the graphic will kind of smush right there, Maniok accent. The heteroscedastic is even more apparent here. That is a small sample size. Statistician might say, well, do we have a good understanding of that scatter? I mean, even up here, it looks to be a higher scatter. There's just more variation for larger parties and what they spend. We probably have a lesser understanding here, but there also looks to be a leveling off. Maybe it's due to kids or something. Maybe higher parties are more likely to have kids. You see very few one-person parties, a lot more two-people parties, and then there's more variation. One person just comes in and gets their steak and leaves for $10. Man, Cheddar's used to have a steak for like $8. It wasn't a bad steak. Can't imagine going out right now and getting a steak for $8. I'd be a little scared. But here's the main deal on Spearman right here. And remember, we talked about Spearman today and how we handle it. How this point right here was the 100th. Oh, join that? Oh, no. How this point in Spearman is not going to be is not going to influence it to an extreme way if we're using Spearman. Does that make sense for this one? And to kind of lightly kind of give more answers, it doesn't really matter if we use Pearson or Spearman right here. I mean, yes, it does. We should use Spearman, but the choice, to be very clear, yes, you should use Spearman right here. Yes, we see a nonlinear, heteroscedastic, monotonic relationship. But when it comes down to it for statistical significance, both the Pearson has a statistically significant p-value and the Spearman has a statistically significant p-value, and both of which via simulations we are convinced that they are statistically significant. We come to conclusive intervals. Pretty much, yeah, I think that's right, Trace, right there. And I'll let you guys look through that output and see if you see similar things. Yours might have maybe outliers. I'd maybe like comment on some outliers. Remember, Spearman handles outliers better. So that's the big deal, is like we've kind of got our notes on like what Spearman does. I'd make comments on like, if you see outliers, Spearman can handle outlier well. Yep. So hopefully that one's making sense. Which one? We'll head back here to Spice. Which question are we going to do next? How are people feeling about that one? I didn't do the exact question you're doing, but I feel like you should be looking at that and being like, I think I know what we're going for on this. The baseball bat just blurs away. What do you think should be next? Hopefully it's making sense. And I'm really just proud of everyone because I can see the progression in people's coding skills, like, and just think it's been like a week and a half, and I really mean it. I tell the story of my student all the time in 320. In some cases, Spearman is significant, but Pearson not, which it's indirect confirmation for nonlinearity. That's some great advice right there. Yeah, you give some excellent advice right there, because if your Pearson's coming back significant, where if your Spearman is coming back significant, where your Pearson is not, then the Spearman, oh my gosh, the Spearman is picking up on some nonlinearity, and that's going to really be it. Or it could be a huge outlier that is destroying the Pearson significance. So maybe something is drastically impacting it, and we were showing this too, because we'll go look at the core demo. Go to the main screen. We can see what can happen with 1 point right here. If you have one extreme point, as in you could have a really good Pearson correlation of like 1, and then you could have one extreme point, and you would get, if you look at this, we're getting I'm trying to get 0. Oh man, so close. So there we go. This 1 point right here, but if you did a Spearman on this Spearman-wise would be very strong still. We could kind of estimate this. If you look at this, we can make a vector of x going from 0.0, let's go 0.2, 0.04, 0.06, 0.08, 0.10, 0.12, and that goes all the way up to 1. What is the length? Oh, we need to end this. What is the length of x right there? 7 values. So now we need to go to y, and y is going to be the values, concatenate. We're just kind of remaking this plot. Yeah, this is all in the reg class. So once again, just library reg class, and then you can run all the code I'm doing, install.packages, and then we'll do the next question here. Install.packages, reg class. This is all thanks to Dr. Petrie right here. Install packages reg class, library reg class, and then you can run the core demo function. And this is all in the CRAN server, so it's widely available. Great questions right there. We basically have the same values, except that over here, this needs to be, and Trace has the next question, it needs to be that. So if we go to plot y tilde x, we should see something similar. I mean, close. And then if we go to associate, I did all right on that. Y tilde x. Here we go right here, and you notice the Spearman is coming back. It looks like maybe just barely. It's a small sample size is the issue. We're getting more statistical significance on the Spearman, so the one outlier is destroying it. Yeah, if you see plot thickening, if you see heteroscedasticity plot thickening, or you see nonlinearity. So think about it. Am I seeing like a nonlinear? Am I seeing plot thickening? Am I seeing outliers? So each of those are marks against. Does that make sense, Michaela? How subject can these answers be? My graph is more linear and seems to be somewhat homoscedastic. Let me take a look. Is this the Tip and Bill one? I'm gonna take a cheat look over here. Let me take a look. I don't want to show it. I just want to. Is it tip? Is it bill in USD and tip in USD? Oh my god. Well, that one. The one I'm looking at. I don't want to quite give it away. Is it Kendall Towel included in the package? Oh, I can't remember that one off the top of my head. I think no. Is that a correlation also? Explain that a little bit in the chat because that one escapes me. I remember learning it. I just can't remember. There's so many things to put in your brain. Go into a little more detail on that one. I don't use that one nearly as much. If you can explain a little more on that. Can you drop your code? Sure. Drop your code and then delete it. I think it's tip and bill, right? Do I have this attached to the global environment? But it wouldn't be, is it? I'm looking at this stuff in the background right here. It's got to be bill in USD, tip in USD, right? I'm seeing things. Yeah. Yeah, and then delete that, Michaela. You're right, 2 seconds. Okay, go ahead and remove the chat real quick. Oh, yeah. I mean, I'm not gonna start. Here, wait. I'm gonna kind of mumble some things. You ready? I mean, you ready? Here we go. Like. Okay, that's all I'm saying. Does everyone get what I'm saying? I'm gonna say it again. You ready? That's all I'm saying. You picking up what I'm saying? You picking up what I'm saying? I'm like, no. Maybe. That's what I'm saying. I mean, there's that. Yeah, is a problem. I could see a status. It's got one of the key aspects. It's got the linear, but I'm leaning. That's why yeah. I want you to pick up on those things because those are all different things that are going to impact it. This is, and people will tell you it's just not a straight decision. You don't just say, well, use this. It's like you look at it and you go, I don't know. That's what you say a lot of times. You say, well, sometimes it's more clear. Sometimes it's very obvious. Sometimes you have a very strong monotonic nonlinear, and then it's like, boom, we know which one to use. And then sometimes you start to see, but you got to be careful. You look at things too much. Statisticians are going to talk either way. You should acknowledge these things at least. Like you should discuss. And then some people might say, well, I don't think those are strong enough. I'm going to stick with Pearson. And then some people might say, I think this is enough to push us over the boundary to Spearman. So correlation coefficient for non-parametric data. The Kendall Towel. Yeah, I should look at that. So non-parametric, not using distributional. Let's ask another question right here. I'm going to take a look at the Kendall Towel, which I just haven't done. Correlation, Kendall Towel rank correlation. So it's rank correlation, which when we do Spearman, it's rank correlation also. And discordant, concordant. I should look over this. Number of concordant points, number of discordant points. Oh, that's cool. So it puts it into quadrants. I haven't done this in so long. I could probably code this. You know what? I should tell Petrie we should code this into the reg class package. So it's going to be... I mean, it looks to be kind of interchangeable with Spearman to me. Looks to be like a Spearman alternative. Like, I don't want to do Spearman today. I'll do Kendall Towel. Yeah, yeah, and they're talking about it handles nonlinear. It looks like they're saying it handles nonlinear, unequal variance. This is a really good graphic on it right here. Ordinal data, here we'll show it. Rank-based correlation, rank correlations. Yeah, and they're saying they're doing them both. It's another rank correlation. So here, let's bring back up. This is why I need to do my adjustments in Windows. Ask another question. This is kind of open floor for questions again. But they're showing the same stuff right here where you have like ordinal data. You've got nonlinear. So ordinal, you could call it monotonic. It just goes up in an order. It's not like saying every point goes up in an order, but you kind of see this this monotonic positive relationship. Outliers, once again, is something we said that Spearman handles. Unequal variances is just another name for plot thickening or heteroscedastic. And then nonlinear right here is another type of, this is still actually ordinal. It's just not a constant ordinal pattern. It's in a sigmoidal pattern. More on sigmoidal when we get to logistic regression. So this is a great kind of summary visually of what we were talking about over here when we said it handles outliers well. So this is a good section here to review. So when we say it handles outliers well, we're talking about, let me try to draw that smaller because we're going to need more space. We're talking about if we have a bunch of points right here, you can have outliers like over here. It's going to handle that well. You walk through question 3, you bet. Let's do some question 3 next. Nonlinear. So you want to handle nonlinear, and it must be monotonic. So that we're going to do this one in red right here, because if you have something that is not monotonic, it's not going to handle this. So that would be a no right there. We're not going to do that. And then handles heteroscedastic. That's what they were talking about there with the unequal spreads. So we'll kind of just redraw their picture where they showed a changing of the spread here at the end. So it's going to handle this heteroscedastic. So really what we were talking about right here literally is this graphic right here with the unequal variances, the ordinal data, which still has a monotonic relationship, nonlinear, sigmoidal, nonlinear. So it is nonlinear, but it's also sigmoidal, S-shaped. That's what sigmoidal means. And we see here that it's still monotonic. And outliers, I wish they made that outlier a little bit stronger. It's actually following the data set right here. Do Pearson and Spearman have to be statistically significant for question 2, part 2, or does it matter which you choose for part 1? Are you talking about... So it's saying right here, I think they're both. Do Pearson and Spearman have to be significant for question 2, part 2? Am I not looking at question 2, part 2? Well, I think the answer is kind of moot, Trace. Does that make sense? Like it's gonna be the same either way. Look, it's the bat just changed colors. What? This is yellow. Why is yellow getting green screened about my green screen? I gotta work on my stuff right here. So I think it and then does the choice versus yep. Does that make sense? I think it should be good on that. We're going to do Mikhail's question. Please tell me if you're still confused on it. But I think right there it's gonna, and then make sure to point that right there. The output of both p-values were what do both have to be? Oh no, it does. No, you could get, and we almost got it. They don't both have to be significant. They pick up on different things. So here, and that's a great question. Then we'll head over to Mikhail's question. We are not getting statistical significance on this. Maybe if we do enough simulations, we will. You're not supposed to do this. Let's change permutations. This is p hacking. All right, let's make the simulations smaller. This is bad statistics. Okay. You want to be that way? There. I want something below 0.05. My gosh. I should put it in a for loop and put it in a while loop and run it while. Really? Okay. You want to be that way? Oh, look at that. Statistical significance. Haha. Thank you. Small permutations. So I played games until I got the p-value I wanted. You can see it's definitely not conclusive with the small amount of permutations that I ran. Just so you can see the code I was running, I ran this with like very limited permutations, which gives me a very poor estimate of what the true p-value is. It's a very wide interval due to the small amount of permutations, which is good conceptually to know. But here we see that the Spearman, which is the rank-based correlation, is statistically significant. Of course, it's super inconclusive on whether or not it's statistically significant. But the Pearson actually is not statistically significant and is conclusive on it not being statistically significant. Now, logically, of course, we want to run this with more permutations, and then we get that this is also not statistically significant, and we are confident of that because the interval is conclusive. And the top one up here is also not statistically significant. So you can sometimes, like, and this was just, it's possible to get something here that is statistically significant and one here that is not. So it just depends on what it's picking up on. I could make a better relationship that would come out better Spearman versus better Pearson and all those different things. I think, here's the thing though, and this is such a great theoretical question, Trace. I would say when your Pearson comes back significant, I think your Spearman will also, because if there's a linear relationship, the ranks are going to have a relationship. So I think it's more possible to get a Spearman that picks up on a nonlinear relationship, but if there is a linear relationship with the Pearson, the Spearman's also going to come back. So, and we use Pearson by default usually until we have evidence like in this one of nonlinearity or something weird with an outlier. And so that's, once again, the perfect graphic they're showing, not right there, where that web page went that I was on, where they're showing this right here where you have an outlier. I usually put my outlier further away from the relationship we're seeing. Great questions right here. Awesome stuff. Let's hop back to space. Let's do this. Here we go. Question 3, how to make those plots. Let's take a look. So there's a lot of ways to make the plot, and I put some good advice on your assignment. Let's go take a look at this right here. You're welcome, Trace. Thank you. Great questions right there. Drink some more coffee. Okay, so you can use the core demo to make plots. And with this right here, here's how I would do it. Here's Brian's advice for making plots. So I'm not going to do all of these. I'm just going to do one of these. So we want a positive linear. Well, let me let you pick. Do you want me to do A, B, C, or D? Do you want A, B, C, or D? I will do one of these, and I'll show you how I would do it. Do you want me to do A, which is a positive linear heteroscedastic relationship? So you got to know positive linear heteroscedastic. You need to, or B, Michaela wants B, negative nonlinear. So it needs to go down but not follow a line. Just think about what's saying. Okay, it needs to have a direction down. So that's part of the things we talk about with correlation is the direction of it, but then it needs to not be well described by a line. So what we're going to do is go to the core demo, and here's what I would do. This is Brian's way of doing it. There's other ways of doing it. My way is I'm going to draw this right here. I'm going to draw a plot. And right now it's linear, but uh-oh, here it goes. Now it's nonlinear. I'm not going to go back up. You could. It wouldn't be the end of the world. So this right now is a negative nonlinear. If you look at the correlation right there, negative nonlinear. I'm going to hit end, and then I'm going to go here to snipping tool, and I'm going to take a picture of this. And I'll probably need to wait till after I knit. This is the safest way to do it. You could save this as a PNG. I could go here to File, save as a PNG in my working directory. Take this name right here, save it as that. Works perfectly fine. That is a great way to knit them in there, but more people run into errors. That would be negative monotonic, correct? And it's still, so I don't necessarily need to draw on these, but I could. You don't need to do this, but it is monotonic because it goes in one direction right here, and it's not linear. So the key aspect is it negative? It is negative because it goes downward. Is it nonlinear? That is correct because it's not well described by just a simple line. It has a negative nonlinear relationship. And so what we need to do here is we need to take this drawing. You don't need the line on or the monotonic nonlinear relationship drawn on it. I would probably go over here to a Word document, and I would just store them in my Word document. And I would keep them over here for when I knit, which means, and this is only if you're doing it my way, I would delete out the graphic thing. If you leave in the graphics, you need to do this. If you use the graphics, the headache comes when I try to model this nonlinear and regression model. Oh, well then, yeah, well, I mean, you might need to put a polynomial in there. That's where you would use the poly function for your x variables. So if you're doing a nonlinear and regression model, which we will be doing at the start of next week, so you'll see that here in Office Hours probably, you would use the poly function as for an x variable, and then you can create a polynomial order. And we can look at that pretty clearly. But no, great questions right there. And you see this a lot of times because this relationship right here, this positive or negative non-monotonic, can be seen pretty quickly. If we look at something like this right here, you can see the outliers. And so this is definitely a Spearman because we got a little bit of heteroscedasticity. It might be due to the lack of points because lack of points means lack of scatter. But you see outliers down here, over here, over here. And once again, the way I was taught to do these things, because this kind of goes back to talking about correlation again. I'll talk for a moment about polynomial nonlinear relationships. The way I was taught to do this was you need to highlight your outliers. I've got a little cluster down here. You need to highlight the form of the relationship and maybe talk a little bit about that scatter. I'm less concerned about the scatter. I'm more concerned, if I'm talking about this one, about the outliers. A little bit of a group of an outliers down there at the bottom. Far outlier on the extreme right, far outlier on the top left. Someone who is very tall and very skinny versus someone on the bottom who is heavier and very short. I'm talking about this individual down here. This is a heavier individual who's very short. This is I think that's a misenter of data. That person is 75 inches tall and 75 pounds. I think they re-entered their data. And so this relationship we're viewing right here is a positive because it goes up. That's positive. That's direction. It is monotonic because it goes in one direction. It is nonlinear because it's not well described by a line. And the strength of it, I could view the strength by looking at the correlation of it. I'm going to go with Spearman. It's moderately strong. I usually say moderate around 50%. I say strong around 75%. So I'm combining the two words to moderately strong. That's completely subjective, what you call it. The strength of it, well described by Spearman, because you notice here the outliers right above my head, the nonlinear relationship. Touch of heteroscedasticity. It's just got a dash of heteroscedasticity on it. One of the first times I lost points in grad school was I called this heteroscedastic, and my teacher was like, well, there's really not that many points. Are you sure that the relationship is changing? Like, maybe if we had more points, we'd see more scatter. And I was like, I don't know. And they're like, well, I don't know either. And I was like, dang it, lost points on that test. So I'll never forget that, Dr. Me. I'll always remember those points I lost. Because I was like, but it's heteroscedastic. It's tighter. It's like, well, there's less points. Less points means less scatter. You remember the points you lose. And then you try to remember the concepts behind it. So this is a moderately strong, positive, monotonic, nonlinear relationship well described by Spearman. Yeah. And now if we switch for a half second right here, we can make an LM of it. And here's the issue. If we fit the line to it, I didn't save into. Just putting this over here. If we fit the line to it, you can see the line has problems up here at the top. So the line starts to kind of go away from it, and we have these outliers. So the question then becomes, what if we fit a polynomial to it? And then we can see what the polynomial fits are. And I did that by appending on a choose order right here. And if you know anything about Akaike's information criteria, we might go with this one right here, or we could look at the adjusted R squared, which is going to be adjusted. So you'll see these are more concepts. I always like throwing these additional concepts just so you can see them, but we can look at the nonlinear relationship here and then use the poly function with a linear model to include a polynomial version of this to add on elements of nonlinearity to the model. Good stuff. What about the interpretation after that? Oh, descriptive model gets a lot tougher. A lot of times, let me put on music here, and keep asking those questions. When it comes to a descriptive model with that, because you're asking like, you know, I mean, I love, when it comes to a descriptive model, I would say what I would do is I would talk about that because you can't interpret the coefficient for the variable easily, because it's not like two individuals who differ by 1 unit of x are expected to differ by blank units of y with their individual that has a higher. I'm going to talk, because this is actually going to be big for next week. Let's talk a major thing right here. This is huge for next week for 320. Let's talk about this. So interpretation is going to be key on the next test. This 320, I know this is not this assignment, but this is huge. Here's the model. Let me visualize it for you. Even though there's some nonlinearity and outliers here, I'm still going to interpret this for the moment. Here's the coefficient of weight. Now, we run into a problem with 201 interpretation. We'll talk about the polynomial here in a second, because that's where things get a little bit weird. You don't want to make this sound cause and effect, because when you interpret the coefficient of weight, what are you saying? You're talking about this model that was created right here to describe these points. So this line right here is describing the relationship and what we would expect and predict for the mean of these points. So the wrong interpretation would be this. This is wrong. Wrong, 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 wrong. You're wrong. Let's see the wrong interpretation. The wrong interpretation is for each pound someone gains, I'm going to go super bad right here, their weight or their height, will increase by 0.07 inches. You're wrong. It's horrible right there. It's a bad interpretation. The right interpretation, and let's just think about why this is wrong right here first. It's wrong because I'm saying if you gain weight, your height will increase. Man, I'd love it if the world works that way. I'd be in the NBA for sure, but we'd all be in the NBA. And people, they'd have to raise the rim up because they'd be like, everyone just keeps growing because everyone keeps eating. The more people eat, the more pounds they gain, the taller they are. It's cause and effect. No, the world doesn't work that way. Unless we're talking about experiments, which we're not talking about experiments here. We have not done a DOE. We're talking about observational studies here and what we observe in this data behind my head. What we observe is two individuals who differ in their weight, by 1 pound are expected to differ in their height by 0.07 inches on average, where the heavier person is expected to be taller. And so everyone take note of this. This is where, if this is a 3-point question, I might give you a half point for this answer. This is a very wrong answer, and we'll be covering this next week. That is a very wrong answer. But if you notice behind my head right here, two individuals who differ in their weight by 1 pound are expected to differ in their heights by 0.07 on average, because that's what we're saying is like, this is the mean for this group, this is the mean for this group. A 1 pound difference, the two individuals, is the same when we add polynomials term. And that's the last little bit right here. If we add a polynomial, which is going to make this way harder, the coefficients, and I'm going to have to build them all, and then we're going to get to Michaela's question. The coefficients really lose. We're going to go poly. The interpretation, I've just never found a good way to interpret this. I've got them stored to the global environment. I don't think the visualize will work on this. So the visualize gets mad. It won't do the poly right here. We can view what the poly looks like. I need to 2 seconds so you can see it. Will that work? Let me take off the poly on this completely. Okay, so that's got that. Let me choose order on it. Okay, the polynomial model you're looking at, let me do this. You'll only see, I wish I could eliminate the other one. I thought it's order. Oh, no, it's max order. It's max.order. There it is. Okay, so there's the polynomial model. So you can see the polynomial model in the background. Let's summarize the polynomial model. And, oh, I never created my m.2. And there's the polynomial model's coefficients. And so here, there's really, I find, not a good, strong, descriptive model interpretation for this to talk about the expected differences. When you talk about this is the polynomial coefficient, and I really have a hard time turning this into a descriptive model. I'd rather use it as a predictive one, and this is a good thing for 324.74, and then we're going to jump to Michaela's question. But does that make sense right here? You can see the polynomial. I wish I could remove the linear model from the background. But it's good. You can see the polynomial model does a better job of picking up at the nonlinear aspect. But when you get into a descriptive model with your B1s, estimates of beta 1s, then, yeah, it's like, well, I don't know how to describe that perfectly well because it's not going to be, two individuals that differ in their weight by 1 pound are expected to differ by. I've never found a good interpretation of that, like to just walk someone through what it actually means for that coefficient, like how it describes the world in a way of what we observe in the data. I mean, I guess you'd have to simultaneously solve the both of them. Michaela says, can we go over the one of the parts of question 5? I'm just wondering how difficult it's going to be to make a plot with the exact correlation values you're asking for. You bet. Michaela, pick one of those questions. Let's do it. So, Michaela, let's go to question 5. And we've got right here question 5. Where's question 5? I'm trying to find it. Here it is. And it's the same sort of thing. We can save the graphics or we can just copy paste them in afterwards into Word. So which one do you want to do? A, B, or C? Let's head back over here to the main screen. So in question 5 right now, we're doing core demo again. So make sure to use core demo. You can use this if you save the graphics with these names. You can use these. If you're not saving the graphics with these names, the PNGs right here, you can delete these and put these into Word afterwards. just make sure they get into your document. Michaela wants to do B, so we are doing B right here. And so if you take a look at what's going on, here we can generate what this looks like. It's probably going to try to find those pictures also. All that special coding right there is like plus or minus stuff. This is the R Markdown viewer. We can hop here to question number, sure, no question 5 spot. Whee! I said, whee! There we go. 5B, if you notice, this is where the image is coming from. And you see it won't pull the image because I don't have it. So I'm just going to say bye-bye to that image. Go away. Generate a scatter plot with a stream of points with an extreme outlier, which is not a word. There we go. I swear outlier is a word. Apparently it doesn't know it, nor does it know scatter plot. Weird what it knows and weird what it doesn't know. Without the outlier, red dot, the stream should have a correlation around this. So the original correlation should be this. This is the original correlation plus or minus this. That's what the LaTeX writing was with the PM, all those different things, plus or minus. And with the outlier, the stream should have a correlation near 0. Save this plot in the same manner you did above and include it. So I'm going to take a screenshot of it, or you could save it using the export functions. Those work perfectly fine also. So I did one very similar to this in class. How would you do it to make a correlation of 0.7? So we want to first make a correlation of this. So I'm going to do just one of these. Oh, I actually had close enough. If you want to make it weaker, you put the points on the outside. If you want to make it stronger, you follow the linear relationship. So you see how I'm able to do that right there. Make it a little bit somewhere in here. Oh, make it a little stronger. A little stronger. A little stronger. Too strong. A little weaker. A little weak. Weak. Oh, that made it stronger. No. There we go. Look at that. So this is, the stream should have a correlation around this. And where do you think I'm going to go? Top left, bottom left, top right, bottom right. Where do you think I'm going to start searching for this point to make it super weak? Do you think I'm going to go up here? I mean, that would make it weak. It's making it weaker over there. Do you think I'm going to go down here? No, that'll make it stronger because that follows the trend in the data. This might do something over here. I mean, that's probably going to make it a little weak. And a little weak. It still kind of pulls it bottom right. Yeah, let's go down here. Ooh, look at that. Negative 0.06. We can do better, though. Negative 0.03. This is the video game to me. This is my life. Come on, 0. Oh, I messed up on that one. Oh, man. Come on. Not fair. Oh, there we got it. And once again, what are we going to do? Once we get this graphic, I like going here to Snipping Tool or Command-Shift-4. We're going to take a screenshot of it. And I would use this method. It's one of the safest methods. I would insert these after knitting, and I would put them over here in my document and insert them after knitting, and you've got your pictures. Just make sure your pictures are there. Oh, yeah, you're talking about distance matrices right there for cluster analysis. I think you're talking about distance matrices with cluster analysis. Correct me if I'm wrong on that. And that would be in 474 where we talk about cluster analysis with distance matrices. I think so, right? You're welcome, Michaela. Excellent work. I believe and we go over Manhattan distance. Let me double check. Throwing all the terms. Is it? I think you might have a typo on it. There's the Manhattan distance. Manhattan distance is, when you talk about it here, I'll hop to space real quick and then I'll talk about that. I feel like, yeah, it's funny. You mentioned a lot of good topics here, and keep asking them because you're stretching my brain. Kendall Tao, I haven't done in so long, but Spearman's going to achieve the same objective. I should look into the differences between the two to better communicate those. Could you go over practical significance? Which one do you want to talk about? What do you want to talk about practical significance on, Trace? And here's a good thing. What do you think we talked about today? So this is kind of, we'll do Trace's question here. Then go more over, are you talking about Manhattan distance? Because Manhattan distance is used in cluster analysis versus Euclidean distance. No, are you not an ANOVA, CANOVA, MANOVA? I should know all these. I don't know every topic in the world. I'm sorry. Keep asking those questions. Just stretching my mind. Ask the big questions. So we are with a little practical significance. What do you think we talked about today? that would really help us talk about practical significance, Trace? What topic do you think we talked about today that would really help us? It's on this screen somewhere. Actually, it's directly on this screen. This is a review slide, but maybe I should have like mentioned this slide. This slide makes it very clear what we're going to talk about here for practical significance to say if it really matters. So what do you think will get us to like this review slide? Actually is very specific and very good on if it's practically significant if we care about it. Correct. Great job, Michaela, right there. Any sort of non-monotonic relationship would be nonlinear because I think a line always has to go in one direction. So as soon as you have something that's non-monotonic, it must be nonlinear. So great question. Anything that is non-monotonic, that means it goes in more than one direction, but then it has to be nonlinear. But if it's nonlinear, it can still be monotonic. Like this one I just drew right there if you're watching right now. That is a nonlinear monotonic. The bottom ones, this is nonlinear monotonic. This is linear monotonic. And this is nonlinear non-monotonic. But if it's linear, it has to be monotonic. R is less than 5%, then there is... so there's no cutoff. Be careful. Don't look at the R for practical. So don't look at the R for practical. What should you look at for practical? So statistical significance is always going to be that p-value. So statistical significance is always going to be the p-value. So statistical significance is always the p-value. But when it comes to practical significance, what are we going to look at for practical a lot of times here? And it'll be kind of this way moving forward. R squared, exactly. So you really have to, interpret it and then say, do I care about this? So when it comes to practical significance, you have to look at the R squared. You have to give it an interpretation. You have to say, do I care? I think it's the hardest part a lot of times is asking, do I care about this? And you'd say here, okay, I know that knowing someone's attractiveness rating would get me 56% of the way to understanding the variation in their friendship potential. And to me, that sounds pretty important. That sounds like, 56% of the variation in someone's friendship potential is attributed to the variation in their attractiveness. So a major component, and this is how I convince people of the practical significance, I'd say a major component, that's what I was looking for. A major component in how much friendship potential people think you have, over half of your friendship potential is apparently explained by how attractive people think you are, which just sucks about our world. Who cares how attractive someone is? This is personal opinions with Brian. Your friendship potential should be based on who you are, not how attractive you are. So this just brings me great sadness for this world right here. Just like, what's going on? But no, this is real data. And apparently when people view you as more attractive, it accounts for 56% of the variation in how much friendship potential they think you have, which is a large portion, over half of your perceived friendship potential of like, I'd like to be friends with that person. They seem like a good maybe not trustworthy. I mean, I want my friends to be trustworthy. Does that make sense? As I go over why and why not I think this is practically significant, as though if you want to win friends, apparently being attractive, according to the data, is part of the way to get friends or to have higher friendship potential. Now, I don't know who, maybe it's not people you want to be friends with, but all the questions we could ask right here. But this is data, sociology data. But does that make sense, Trace, right here? We have to make the case for why we care about it or not. So whenever you're talking about practical significance, you're really talking about R squared right here. And you have to explain to someone. Like we do one more right here. Let's go right here. Let's look at some height weight and look at the p-value on that. Okay. So we're just going to do some classic height weight stuff right here. And look at the p-value on it. Where's my height weight? I had the associate on it earlier. There we go. Okay. So if you go get the R squared of this, we're just going to use correlation, not rank. I know it's got some heteroscedastic. Mental just yeah, that's what I was. Yeah, I knew. Yeah. Let me look at that here in a half second. Or we'll look at that next. 36% of the variation in your height is explained by the variation in your weight. So, you know, when a ride says like a certain weight limit, they're probably also going for a certain height limit, because if you understand someone's weight, according to this data, you would have 36% of the information needed to know their height. That's what we're talking about with R-squareds, how much information in height we understand by knowing weight. It also goes with sum squares reduction, all those things coming up soon. But weight seems to be a very valuable variable, getting us more than 1/3 of the way to understanding someone's height. There's probably other things that come into play, like someone's gender or the height of their parents, or I'm trying to think what else would explain someone's height. Probably gender, height of parents. And you could easily do these things, especially with a linear model right here. Like here we are just looking at the linear model. Let's look at the summary of it. And R-squared is going to be very important moving forward, because you see here an R-squared of 36%, which is what we just calculated a half second ago. And we could see here a better model, which incorporates gender, is going to explain 56%. So now we've explained more of the variation. We can also visualize this pretty quickly to see that we have more of the variation explained when we look at this right here by including gender in the model. We could also include the interaction between gender and weight and see if that increases the R-squared. R-squared of 56, so it looks like that really didn't help. And you notice the model, really, the interaction term is not coming into play much. I wouldn't say determines, I would say is associated with or explains. It's like we can understand, in this instance, I understand 56.81% of the variation in someone's height by using this model. Like, the model explains 56.81% of the variation. It's not like it's determined by, like, that sounds a little too cause and effect. Does that make sense? I probably would look at that on the test and I'd be like, okay, close enough. This is where just statisticians get picky about wording. And I would say, you know, is attributed to, is explained by knowing someone's height, and by knowing someone's weight, and by knowing someone's gender. And this is like an advanced question right now. We would get 56.81% of the way to understanding the variation in someone's height. You know what? The determines by, I'm not so bugged by that much more as I think about it. It's like determined by is explained by. Not that big of a deal. I'd look at it and I'd say, yeah, it's good enough. And you see the interaction term is not statistically significant. Hence why don't see much of a difference between the slopes of the line coming up later. A lot of things you're seeing as I kind of show different things are just like examples of things that will come later in class. Yes, I do know this term. So moving forward with practical, yes, trace, huge thing right there. Moving forward with practical significance, it's going to be very important to look at the R-squared. R-squared is going to be super important. I know this term. Yes. Okay, I'm looking at it. It looks to be like eigenvector space stuff, because I'm seeing right angle eigenvector stuff. Yeah, it's cluster analysis. Cluster analysis, it looks like. Multivariate outlier detection is talking about. It's not cluster analysis, maybe? I've used it, I just haven't used it lately. Montelobos distance is a measure of distance between a point P and a distribution D. Multi-dimensional generalization of the idea of measuring how many standard deviations away P is from the mean of D. The distance of P at the mean of D grows as P moves further away from the mean to principal component axis. Oh, it's principal component analysis. If each of these, yeah, that's why it's using eigenvectors. If each of these axes is rescaled to have a unit variance, then the Montelobos distance corresponds to standard Euclidean distance in the transformed space. The Montelobos distance is thus unitless, so it's like a z-score. It's unitless. Scale invariant, doesn't matter what. Yeah, so doesn't matter if we do it with height, weight, units, pounds, whatever. It takes into account the correlations of the data set. So it looks, so it's outlier detection, right? So it's a unitless. What about collinearity between weight and gender? Yep. Mm-hmm. Well, actually, yeah, let's talk about that real briefly here. Talking about some variance inflation, multicollinearity, collinearity right now, not multicollinearity. These are such great questions. You know your stuff. And we're at the end of office hours, so please ask those questions. So yeah, the way we do outlier detection right now specifically, and I'll just show you right here, we have an influence, and we go over what these terms are. So the way we do our outlier detection is with the following. We've got here the leverage, And we've got here the deleted studentized residual, and the leverage is going to be found via Cook's distance. And then the deleted studentized residual is going to be the deleted studentized residual. I could go into more points on that, but it's a residual that is going to be we're going to remove the point and look at the line without it. I can lecture on it if you want. But the deleted studentized residual. Studentized just means it's been standardized, and studentized for William Gossett's student T distribution. So kind of like standardized, but studentized. And then deleted means we've removed the point to look at the line's influence or the line without it and calculating a residual by not having the point's influence there. The leverage is how far away something is from the mean of the x's, so you're still getting this kind of multivariate sense where points at 0 are going to be towards the mean of the x. They're going to be in this region, and the points further away up here on the top boundary versus down here on the lower boundary are going to be points of higher leverage. Like this point right here could technically be, it's probably that point over here. That's got higher leverage. That is the female, no, it's the male distribution. So it's probably that point. Yeah, if you look. And then there's 2 points further out. No, it can't be that point. I don't know if it's showing every single point. It's hard to determine what point that is. Yeah, I don't know which point that is. Tough seeing it. Let's make it easier to look at. Let's just do height and weight for the moment and look at the influence plot on this. Okay. So now we've got 2 points down here, got the points out here. If we visualize this just to see better, you'll notice the 2 points over here, 1, 2. This one's going to have a little more deleted studentized residual, and you see that right here, but this one's very close to the line, giving it a very small deleted studentized residual. But this point back here, that's all the way back here, is actually up here. It's not towards the left side because this is what is considered high leverage. And high leverage would be further from the mean of the x's, and this point actually has some leverage, it's further away. I'm going to go into way more detail on this. The last topic you're bringing up there is kind of the idea of collinearity and multicollinearity. Collinearity is the door to multicollinearity, because when we're talking about collinearity, we're asking what is the shared variation, or what is the variation in weight explained by gender. So you can actually take a look at this by creating the model right here, and we should get... Is it going to do it if I do that? Yep. Is it not like it because it's... We may have to switch this around a little bit here. Oh, gosh. I'm not doing tilde. There we go. Now, this is a lot of work for a concept right here that we're doing. But this concept right here, the r squared of this model, and I want you to take a look. This is an advanced topic. We will be covering this start of a week from now. Not next week, but 9-10 days from now we'll be covering this. This is a multiple regression talk. What have I done right here with, we have a multiple model. And then what have we done right here? This is a model where I've taken my 2 whats. Like in this new model right here, and we'll call it, here's a hint. Let's call it sure, which basically gives away what it is. What have I done right here with this new multiple model? Or not, it's no longer a multiple model, but it's a model where one of my whats is explaining the other what. Does that make sense? This on line 10 is a model where one of my x's is explaining my other x. So we're seeing, does gender explain weight? And we don't want to see that. We'll definitely be talking about this with the multiple world, the idea of collinearity, and then multicollinearity is just how does one x get explained by multiple x's. And so this is the relationship between x's. And so we're going to look at this right here and get the summary on it. And what's really interesting is this r squared is not good. That is the collinearity. That weight, 34.7% of the variation in weight is explained by gender. But we don't want our x's to be explaining each other because that creates confusion in the model. More on variance inflation in a half second. I'm not going to go into too big detail. Remember, anything I'm talking about right now, we're going to go and talk about for 20, 30 minutes and do lots of examples on. So we have here the variance inflation of the original model of, oh, because I overwrote over it. The variance inflation of the model right here, which actually is not that bad, but I mean, this is not that great of a model. But how is this being calculated right here? If you notice, it's the same because it's just a 2-variable x model. So it's just how does gender get explained by weight and how does weight get explained by gender is creating this variance inflation right here. The variance inflation factor is actually calculated by the formula 1 over 1 minus r squared sub I. The r squared sub I is how the ith x is explained by the other x's. So guess what? Right here, I plug this in. We plug in the r squared right there, and it might not have carried enough decimals, but it looks close enough. This is how this value is being calculated by finding the variation in our x's explained by our other x's, and then calculating the variance inflation factor, which this is the increased amount of uncertainty we would have in the standard error, and it's squared, the standard error squared. Really good questions, pretty advanced. We've done a lot of work on the assignment today. Any last questions? But this is not a good thing. We can quickly examine variance inflation factor. Like if we just do something crazy right here, oh, it's super mad. Oh, comma data equals survey 10. There we go. Now it's no longer mad. You want to talk about some variance inflation? There's some variance inflation for you. Really? Oh, not that bad variance inflation. And it's doing the generalized variance inflation factor right there. So, but not too bad. Let's go here and go to, really? I'm just shocked you didn't get that crazy variance inflation. And then we'll have a standard. We'll go into way more detail on this. Way more detail on this to come, everyone. Well, that's got it. If you can tell, these topics are widely used, and I really like it. A lot of the things you see me mentioning here are things we cover that we'll go into big detail on. If you see me talking about something right there and you just watch that part of the video, you're like, I have no idea what Brian's talking about. Multiple model, linear model, we haven't done that stuff yet. We will spend whole days talking about these things. We'll have a good 100-minute class going over what is variance inflation, what is leverage, what is deleted studentized residual, and we'll do more examples. We'll hop through these examples. We'll talk about these concepts because these are things, if you can tell, they're not just used in our class. They're widely used, medical industry, finance industry, economics, sports. All these different concepts are used to understand data and the relationship within the data. I think that's got it. Probably did, if Trace, Michaela, if you're still here, how far are people in the assignment? We got 2 viewers, probably me and someone else. I hope people got pretty far with the assignment. People were asking about question number 5, so maybe people are done. People are like, assignment comes out today, finish it by 3 p.m. today, done with the assignment, good to go. With that, we'll be back on Monday. We'll be back this weekend also. I'll see everyone later. Bye for now, everyone.